Hello, good afternoon, everyone. Today I'm happy to have Xiaohang Chen give a seminar here and online. Although Xiaohang is now a postdoc at University of Michigan. He got his PhD from University of Arizona last year, working with Joe Giacalani. Xiaohang's research focuses on solar energetic particles based on my understanding from theoretical, numerical, and observational aspects, so including three, most of the three aspects. And then today, he will share us a study about numerical simulations of the 2022 Labor Day event observed by Parker Solar Probe. And let me pass it to Xiaohang.
Yeah, thank you, Bing. Let me share screen now. Okay, I hope you're seeing the right screen, right?
Yes.
Okay, great. Yeah, thanks again for inviting me here to talk about our recent research about the numerical simulation of the Labor Day event. Because it's close to Labor Day, so people usually name it the Labor Day event. And this is a very interesting event because it's one of the most intense SCP events in the current solar cycle. And it's also the closest ever SCP event we have seen from the Parker probe. It's about 14 solar radii. And there are a lot of interesting features, and we believe these features can improve or potentially improve our understanding about the physics of SCP acceleration and transport in the solar heliosphere. But before jump to the observations, I'd like to give a very brief introduction about the solar energy particles. So solar energy particles are high energy particles, usually from a field keV to about GeV, that accelerate in some explosive phenomena near the sun, such as the solar flares and the coronal mass injections. And in some very intense SCP events, they can potentially pose the radiation hazard to the human and the equipment in space. And in this large events, the high energy particle can penetrate through the magnetosphere and get into the atmosphere of the Earth and produce secondary neutron particles that can be detected on the ground-based detector. And in these large events, the aurora can extend very low latitude. I remember in the SCP events last year, some of my friends came at the Grand Canyon. They can even see the aurora there. And also they can lead to massive power outage, like the Halloween event in history. So historically, the SCPs are believed to be accelerated, originated from the solar flares, because at that time people don't have the in situ observations, and they find quite good correlation between the flares and then followed by the geomagnetic storms, because that's the only phenomenon we can observe on the ground. But later in the early 90s, due to this more and more in situ observations, we observe another feature, what we call the coronal mass injections. And we found that the most of large SCP events are usually associated with these features. So now we have a better understanding of this SCP event. Basically, they can classify it into the gradual SCP event, the left panel issues, and the impulsive SCP event, based on the acceleration mechanism and origins. So for the gradual event, particles or SCPs are believed to be accelerated by the shock driven by the coronal mass injections. And in this event, this handed particle can last for a few days. That's the reason why it's called gradual. And the energy is pretty high. It can go up to GeV. And the main components of these particles are protons, because these particles are accelerated by the shock from the sun to the Earth. The main composition is from the solar wind. But for the impulsive event, particles are believed to be accelerated in the reconnection in the solar flares. And this event usually features with a very sharp spike, and particle arrive at the observer detector, and then they quickly decay away. The main component, the energy of these particles usually can go up to MeV, but never to GeV. And there's a lot of heavy ions in this event, which suggests that these particles accelerate near in the lower solar atmosphere. So from the space weather concerns, the gradual events attract much more attentions because the particles' energy are higher and they can distribute over a broad range of heating longitude due to the shock distribution. Then how can these particles be accelerated by the shock? The widely accepted mechanism is called diffusive shock acceleration. And in these scenarios, particles can be accelerated by the shock very efficiently, and it's also highly depend on the geometry of the shock. So in the left figure shows the blue plane is the location of the shock. If we define the normal direction of the is the direction it is what we call the shock normal is the direction that's perpendicular to the shock plane. And if the upstream magnetic field is perpendicular to the shock normal, then we call this shock is the perpendicular shock. And in this condition, if the particle has a larger enough energy, then the geo radius of the particle is larger than the thickness of shock. So particle can do geo motion along field line, and also due to because of this larger radius, particle can cross the shock multiple times along shock surface. And due to the ground large magnetic gradients across the shock, this particle will do drift motion along shock surface. And each time particle cross the shock surface, it will be accelerated by this convection electric field. And this is a very efficient way to accelerate particle to very high energy because the geo frequency is very small for this, is very geo period very small for these particles. Another scenario is what we call the first order Fermi acceleration. So in this scenario, the shock is what we call parallel shock. The shock normal is parallel to the upstream magnetic field. So particle can be scattered by the magnetic turbines in the solar wind back force across shock. So this is the wave particle interaction or the not the particle interaction. We can understand this phenomenon if we imagine there's a ball hitting to a moving ball toward this ball. And when the ball gets reflected, the energy, the velocity in the inertial frame will increase with which is the initial velocity plus the velocity of the ball. And another easy way to understand this phenomenon is that if you imagine a ping pong ball is bouncing between the wall and the racket, and you're gradually moving the racket toward the wall, the ping pong ball will bouncing faster and faster. And this phenomenon is, this mechanism is what we call the first order Fermi acceleration. So if the particle can move in random work in upstream and downstream, and it has a possibility to cross the shock. And each time the particle crosses the shock, it will be accelerated by the electric field. So all this, both of this mechanism can be summarized into the diffusive shock acceleration, and this can be quantitatively described by the transport equation. It can either be the Parker transport equation or the Fokker transport equation. So in this transport equation, it includes most micro transport effects here, so such as the advection with the solar wind, the diffusion in the turbulent field, the curvature and gradient drift, and also the energy change due to the compression or rarefaction across the shock. And if we consider 1D geometry, and then we can get the analytical solution of this equation. This is the solution of the distribution function of the particles. Generally, we can get a power law distribution. and the polar index only depend on the jump condition or the density difference in the upstream and downstream. But the energy cannot go to infinity. There's always a rollover at the energy part, and it's basically related to a number of factors regarding the shock geometry or the acceleration time and the escaping condition. But basically, it's always related to the how well the particle are trapped at the shock. If the particle are well trapped at the shock, then they have the more chance to be accelerated to higher energy. But also, as mentioned, the shock geometry plays an important role in this diffusive shock acceleration theory. And it's described by the factor what we call the diffusion tensor or diffusion coefficient. And generally, in the perpendicular geometry, the diffusion coefficient is much smaller than the parallel diffusion coefficient. This value can also understand as the mean-free path of the particles. So, and also theoretical studies have shown that the acceleration rate of the how fast or efficient the particle accelerate at shock scales inversely with the diffusion coefficient, the value of this parameter. So basically, this was to say the perpendicular shocks can accelerate particle much more efficient than the parallel shock. But in reality, the shock geometry is not that simple. It can vary significantly along the shock surface. And this figure shows our previous work about how the shock evolution of the shock geometry affected the particle acceleration and the distribution in space. And also, we have seen a significant longitude variation in this large SCP event. So basically, we have wide separated the spacecraft in space, and this spacecraft detected this SCP event almost simultaneously at different locations, but the intensity profile looks quite different. So there's some spacecraft observe a very quick onset of the SCPs, and some spacecraft observe a gradual increase. And we believe this is related to the transport and acceleration process when the shock propagate from the sun to the observer. What a typical large SCP looks like? So the right lower panel shows one of the large SCP events has been observed from ACE, the ACE SOHO and the STIR A. So basically, for these high energy particles, they usually accelerate near the stem and the transport to observer because the energy is really large, and so this observer always detect a very quick onset of these particles. And also there's likely to be electron contamination in the lower energy part. And this NH, SCP NH gradually, intensity gradually increase and peak at the shock. So this peak is what we call the energetic storm particle, or ESP. And these particles are believed to be accelerated locally by the shock. And after passage of the shock, we see that the intensity of all energies gradually decrease in the downstream. But in the Liberty event, we see something really different from the PSP observations, and we believe it can expand or potentially improve our understanding of the diffusive shock acceleration theory. So for this event, the black arrow shows the eruption direction of the CMEs of this CME, and the Parkinson probe is located really close to the sun. It's about at its perihelion. So the PSP is about 14 solar radii. It's the closest ever SCP event we have ever seen. And also the solar orbiter have a quite good aligned with the direction eruption of the CME. So, and the solar orbiter sees about SCPs of the NH about 100 MeV. It's a really intense SCP event. I call it one of the most intense SCP events, but I likely I'm more likely to call it most intense in the current solar cycle. But if the SCP because this semi erupt on the backside of the sun, so the solar orbiter, the solar hole is and the stellar A didn't really see any SCPs. But if the semi eruption in opposite way, it's likely to be a ground level enhancement event and it can pose a great threat to the spacecraft in space. And the right figure shows the white light image of from the silver A, and it's general. This is also include the location of the PSP, so it's really close to the sun, and also the shock surface. So here is the Paxil probe observation from the ESIS instrument, which is a high energy particle detector on board PSP. It's from the AP low to AP high, it's covered energy range from about 60 keV to over about 80 MeV. So from the lower panel show the scientist profile of the SCPs of low energy, and what's interesting things here is that we see what we call inverse velocity dispersion, which means that for this first arriving particles, in the regular SCP event, we always see the high energy particle arrive first, then gradually followed by these low energy particles. But because this is just because the high energy particle moving faster than the lower energy particle, and it takes a shorter time to propagate from the shock to the observer. But for this event, we see that we see the first arriving particle located about MeV, and then the high energy particle arrive even later than this lower energy particles, which is very abnormal. And another interesting features is that we see that the before the shock, the particle in the upstream, the highest and maximum energy of this SCPs is about 20 MeV. But in the downstream of the shock, so this is passenger of the shock. In the downstream, the energy even increased to about 60 MeV, which is also we can't expand in the regular DSA theory, because there's nothing can accelerate particles locally in the downstream from 20 MeV to 60 MeV. That's really a large energy jump, not the 20 keV to 60 keV. And so this is the observation of a solar orbiter. So what we observe in solar orbiter is consistent with our regular DSA prediction. So this plot reminds you where's the location of the solar orbiter. It's located at about 0.7 AU. So the maximum energy observed by solar orbiter is extremely high. It's about over 100 MeV, and this is just the limitation of the detector. And we see a regular velocity dispersion here of this first arriving particles. That's a high energy particle arrive first, then gradually followed by low energy particles. So how to explain this difference? There's a lot of puzzles in these observations. So first, there's the inverse energy velocity dispersion, where the low energy arrive first, then followed by the high energy in the PSV observations. And before the shock, in the upstream of the shock, the maximum and SCP energy observed by PSP is about 20 to 30 MeV. But for the solar orbiter, it can go up to 100 MeV. And in the downstream, after the passenger of the shock, the maximum SCP energy at PSP increased to about 60 MeV, and the maximum energy of solar orbiter gradually decayed in the downstream. And also, there's no SCPs, obvious SCP detection features at the SOHO or ACE. So to understand this difference or these observations, we try to do data-driven SCP simulations. So the first step, what we do here is we use the model called ellipsoid fitting model, that it fit the structure of the CME based on the white light image from different point of view. So for this event, this is another event, but it's used to illustrate how this works. So this event, they use the white light image from the Steel B, SOHO, and SDO and Steel A. But for the Liberty event, we lost the observation from Steel B, but we still try to characterize the shape of the CME. And basically, this image output can be output at 10 series, like I remember it's 12 minutes per image. And by fitting the shape of the CME for all these images, we are able to illustrate how the shock geometry evolve in space and time. And then we put this shock into the MHD simulation of the background solar wind. So here is the background solar wind from the Olsen R model of University of Michigan. It's a data-driven MHD simulation of the heliosphere. And with this setup, we are able to extract the shock parameters and plasma parameters at the shock surface. So the right panel shows the distribution of the Alphen magnetosonic Mach number. Sorry, this is magnetosonic Mach number distribution on the surface of this ellipsoid, or you can view it's the surface of the shock. And we can also establish the magnetic connection from the spacecraft to the shock. And this is the oops. I think this is a movie, but okay, it's fine. It's a picture. Never mind. So basically, we can characterize the evolution of the shock surface, and we can extract the shock parameter at the intersection between the shock surface and the fuel line connect to each spacecraft. This is the right panel shows how this parameter evolve as a function of the radial distance. And the blue line represents the shock parameter connect to axial probe, and the red line represents the shock parameters or plasma parameters connect to solar orbiter. We can see that it's very clear that because the solar orbiter is located in some low Alphen speed region, and if we consider the shock speed, it will give rise to a very large Alphen Mach number. So the blue line is here. Sorry, the red line is the Alphen Mach number connected to the solar orbiter. And also PSP is located in some really high Alphen speed region, and this region is generally characterized by the higher magnetic field strengths and lower density, and that's the reason why we see this Alphen Mach number is much lower than the solar orbiter, and this is in log scale. If it's linear scale, it's tens of magnitude. And then also we characterize the shock geometry, the theta BM. The theta BM is the angle between the upstream magnetic field and the shock normal. It's generally characterized the shock geometry as we just discussed, if it is a parallel shock or perpendicular shock. And with these parameters, we can also use the jump condition, MHD jump condition, to calculate the density jump across the shock. So the red line represents the density jump at the solar orbiter, and the blue line is the density jump connecting to the axial probe. And we can see that below about 5 star radii, the density jump is always below 1, which means that in this region, the shock can not separate particles. And but the solar orbiter, it's the compression ratio jump very quickly, and that's the reason why we see the energy difference of this maximal energy SCPs. So solar orbiter sees over 100 MeV particles. That is likely because the shock, the spacecraft is connected to some strong shock region near the sun, and particle can be very efficient here and propagate to solar orbiter. But for the PSP, we see that the spacecraft is connected to some relatively weaker shock. So the particle cannot really be accelerated very efficiently. And that's the reason why we don't see, we see the particle energy only about 20 MeV. And also these features also contribute to the inverse velocity dispersion that we just discussed. And I will catch up later. And we also try to simulate the CME with the actual MHD model. So this is the CME model simulation we just performed with the image model. And it's a real-time simulation. So the blue dot represents the location of the Paxil probe, and the right dot is the location of the solar orbiter. And the blue dot is the green dot is the location of the Earth. So initially we can see that the shock past the PSP at the flank about the flank. And the shock and in the observation we see that the shock geometry is about 50 degree at the theta beam, and this can kind of consistent with our models. And then we also try to extract the surface of the shock based on this simulation, so that we can perform the similar analysis with that elliptical fitting, which correlate the shape of the shock based on the white light image. But now we can do the actual CME simulation to see how the shock surface involved in space and time. So in this simulation, we can see what we plot here is the compression ratio, or we call the density jump, the downstream density versus the upstream density. We can see that initially this blue line is the field line connecting to PSP. It's connect to some region with relatively lower compression ratio. But because the PSP is moving very fast near perihelion, so this line gradually shift to this hot region on the shock surface. And this the right panel is another view of the shock surface later. So we can see that this blue line has really connect to the strong large compression region on the shock surface. And this red line is the manifold line connect to the solar orbiter. Okay, it's always connect to the shock strong shock region, and that's the reason why we see the energy difference in this two spacecraft observations. And then we try to use this simulation to expand why we see this energy increase in the downstream of Paxil probe observations. Because currently there's no way to accelerate particles across several MeV in the downstream. There might be turbulence of the stochastic heating, but never to be able to accelerate particle to about 60 MeV. So that's the puzzle of the PSP observations. How can particle increase energy in the downstream? But with our model, we can see that initially in the upstream, the PSP is connected to the weak shock region. And the particle observed here is accelerated from the shock at these regions. But the aftershock past PSP, because the PSP is near the perihelion, so it's moving really fast, and the connection to the shock can change dramatically from this weak shock region to strong shock region, and the particle accelerated from this strong shock can transport away from the sun as well as toward the sun, and the PSP is likely to observe these particles in this way. And also, we analyze the anisotropy of these SCP intensities. So these two panels shows the SP detector from the head A and head B. Well, head A is the detector collecting particle moving away from the sun, and the head B is collecting particle moving toward the sun. And we can see that the intensity from hit B is relatively larger than the hit A, which means that the majority of these particles can kind of moving toward the sun instead of away from the sun. And this is another support of this hypothesis. And we try to analyze these features more carefully. And there's another this blank region because this is a so strong event that the PSP changed to dynamic threshold to protect the instrument. So there's no data in this this white regions. But there's another very small pixel detector that's always on during this event. It's collect the particle from a single pixel detector, but it has also have the detector on A side and B side. We try to use this to characterize the anisotropy of these SEPs at this energy increase and also in the no data gap region. So we see that A side, the ratio of this intensity of A side over B side is actually lower one during this energy increase period. And that's direct evidence shows that this particle actually coming toward the sun, not away from the sun. And we use this, I just draw these pictures before the meeting, try to illustrate my hypothesis. So basically, so initially the PSP is the cross the wake shock region when the CME pass the detector. So that the NH, the SP detect here is about 20 MeV, is relatively lower. But because the PSP is moving extremely fast in perihelion, so it can move to some region that's connect to the strong shock region. And the particle accelerate here, it have a much higher energy, and it can propagate away from the sun and toward the sun. And what we see is the energy increase is the one particle, one PSP enter this region and start to detect the particle accelerates from this strong shock. Then we try to do the actual particle simulation. So here, what we do here is that we use the stochastic differential equation of the particle equation to simulate the particle propagation, or what we call the pseudo particle distribution, based on the parameter we just obtained from the data-driven MHD and observations. And there's another important factor, what is the diffusion coefficient. This is another work which is published. We try to characterize how the diffusion coefficient or mean free path of the particle evolve as function of the radial distance. So we use about 9 solar Park-Solar probe orbit and use the actual manifold measurements to calculate how this diffusion coefficient evolve in space. And this is the empirical formula we obtained from this this work. It can generate describe how the diffusion coefficient evolve as function of the radial distance as well as the energy of the particles. We use this formula in our particle model, and we try to simulate the time intensity profile of the SCPs. So the left figure shows the simulation result. We try to collect the particles from different star radii and see how the particle, how the intensity profile evolve as function of radial distance. So the top panel, followed by the left figure shows the SP time intensity profile detected from about 8 star radii to about 14 star radii. So here is the location of the Park-Solar probe. We can clearly see that there's no features of these SCPs, and it's gradually evolve much gradually sharper and sharper as the shock propagate outward. And we can also see this inverse velocity dispersion in our model. So how can we understand these features? Basically, the DSA, the diffusive shock acceleration theory, predict the particles take some time to be accelerated from certain NH to higher NH, and this time is what we call the acceleration time. And it's depend on number of factors that's the jump compression ratio, the upstream solid wind speed, and as well as the diffusion coefficient. And because the PSP is connected to a relatively weak shock, and so the shock takes longer time to accelerate particle to very high energy, and that's this is the figures from Matthew, and Matt and Joe are also working on this problem. They have another parallel work is going to be submitted soon, and this right line characterize how the highest energy can be accelerated based on this A, and it kind of limited the maximal energy of this sentence provides. And the green line characterize the velocity dispersion. Basically, is described when the high energy particle arrive, and then followed by the low energy particles. So there's a computation between the acceleration time and the shock propagating time. So for example, the shock can accelerate particle above 100 keV at a certain location, and as shock propagate outward, the particle can be accelerated to higher higher energy, and the time to accelerate particle to high energy is comparable to the time when shock propagate a certain radial distance to another radial distance. If these two times are comparable, then we are likely to see this inverse velocity dispersion. And there is also a direct evidence for this undergoing particle acceleration at the shock. And then this is the summary of our work. So we based on our simulations, we kind of be able to explain the nose features of the inverse velocity dispersion features in the 10 profile observed by Parkinson probe. Basically, this is because of the computation of acceleration time and shock propagation time. If the shock is connected to some relatively weak shock region, or if the shock is close to the sun, we are more likely to observe these features. And we can expand why the PSP observe relatively lower NH compared to solar beater. This is because the PSP is connected to the shock regions with smaller compression ratio, so the particle cannot be accelerated to very efficient to accelerate to high energies. But the solar beater is connected to the large compression ratio regions, which means the shock is stronger here, and the particle can be accelerated very rapidly to high energy. That's the reason why we see the SCP is above 100 MeV. And the PSP, we also can able to expand why the energy increase in the downstream. This is because the PSP is moving extremely fast near perihelion, and it's connected to the strong shock region in the downstream. And the behind the particles accelerate in this region can propagate toward the sun, and that's the reason why we see this SCP energy increase in the downstream in PSP observations. And also, our model shows that the Earth is not really meant to connect to the shock surface because it's on the backside. And so that's the reason why we don't see any SCPs, and we can use this model to predict where is a region to likely see more high energy SCPs, where is the region we probably won't see SCPs. That's pretty much of my work, and I'm open to any questions. Thank you so much.
Do we have any
Thank you,
questions?
Xiaohang. I have a few questions, but maybe we can
No,
I can wait for the in situ people first, not in person audience first.
think here, no, right, yeah, you can go ahead. Go ahead.
Okay, thank you. So, Xiaohang, maybe a few questions. One is I'm not familiar with that part. You mentioned that if the compression ratio is lower than 1, then the shock cannot accelerate particles. Do you mean there's no
Yes.
particles being accelerated, or maybe
So
not high energy particles?
no, the shock accelerate particle because of a compression. So if there's a compression, then there's a manifold
Yeah.
gradient, and there's a velocity
Yeah.
gradient across shock. And that's the reason why particle can be accelerated. But if the compression ratio below 1 or equals 1, so if it's below 1, we just assume it's 1 because there's no density. So this is an analytical solution from the jump condition. It can predict it's give a result of compression between 1 to 4. So if it's below 1 or equals 1, it means that there's no compression across these two regions. So that's in our world, there's no field gradient, no velocity gradient. So the particle cannot be accelerated. It's just in the regular solar wind. But if it's above 1, it means there's a compression there. So the particle can be accelerated.
Yeah, good. And then for maybe for your simulations, or maybe just what you mentioned, that's why you see inverse velocity dispersion is maybe one reason is due to the acceleration process is still ongoing when the shock propagates outward, right?
Right.
So because you also have solar orbiter data there. So have you compare, or maybe just because solar orbiter can see an potent at very high energies, so have you tried to see if those high energies get maybe a later release time? Because, for example, like initially those particles are not as efficient, then at solar orbiter you won't see.
Yeah, because the solar orbiter is located quite far from the sun, so these nose features can be erased by the transport process. For example, you can see the nose is very clear when it's already but it's become sharper and sharper here, and after beyond this region, because the high energy particle propagate faster than the low energy particles, so this inverse velocity dispersion, this high energy particle can gradually catch up the particle, the lower energy particle ahead of him, and then at about solar orbiter region, we are more likely to see the regular velocity dispersion because the high energy particles have already catch up the low energy particles, and it's arrived earlier than the low energy particles. But we also do the solar orbiter simulation, and we do see the regular velocity dispersion here at that region. But if we place the detector really close to the sun, we also be able to see these nose features.
Okay. Yeah. And maybe I would like to hear one general comment from you is maybe, for example, for particles at relatively high energies, for example, around 100 MeV, at which distance you think those particles are being efficiently accelerated and then released?
Well, it can be different event by events. It's basically depends
in
on the
general, maybe.
I would say if the compression ratio is large, like solar orbiter, about 4, close to 4, and it's likely to be accelerated to 100 MeV, very close to the sun, like the several solar radii.
Okay.
And this is cool. And by the way, I'd like to mention that the solar orbiter also see this inverse velocity dispersions in some real case. And we try to propose that the solar orbiter is located in some relatively high upper speed region, and this will make the shock compression ratio or upper Mach number relatively lower. And in this way, the particle takes a longer time to be accelerated, and is comparable to the time shock transport from sun to solar orbiter. And in those events, the SCP-NH not high. It's about MeV particles. We never see the 100 MeV particles show this. All the very strong SCP events show these features, and it's also illustrate that the SCP acceleration that highly depend on the upstream solar wind conditions. It's depend on where the spacecraft is mainly connected. If it's inside like corona hole or many heliospheric current sheet, and the acceleration efficiency could be quite different.
Great, thank you.
Right, any, don't think we have any other question. Maybe I have one now. Do you mean like the particles, the high energy particles seen by solar orbiter? I mean, you mean those and on those that you show, those particles can reach the lower energy one, and then we can see that shape one that is inverse in races. Are you talking about the same particles that you can see with the Parker solar probes and then with the solar orbiter, or there are different acceleration processes going on, and then we see the solar orbiter?
Yeah, so if we put the solar orbiter really close to the sun, and the shock takes a much shorter time to propagate to the detector, and is comparable to the acceleration time used to accelerate particle to MeV, then we are likely to see the shock nose features. But because the particle's energy is so high, about MeV, so it's moving about the speed of light. It's a kind of catch up the low energy particle really fast, really shortly. And then if we put the detector a little bit further, we are likely won't able to see this inverse velocity dispersion, but instead it's we observe is the regular velocity dispersion.
I see. All right.